Energy balances with reactions are important for many systems. Here's, for example, a power plant. Today we're going to cover two main items. First, an energy balance with a single reaction, being able to compute delta heat of reaction or the enthalpy of reaction. And then we also have the energy balance with delta H of formation, and we're going to use that for multiple reactions. Okay, so let's just do an example problem first of all. Now this example problem is just the reaction A goes to B. Okay, and we want to be able to compute the delta H of reaction for this case. Okay, so let me go over to some notes here. Okay. And I'll just create a new page. Okay, so we have so let's say we have A goes to 2B, and we're going to have a certain number of moles coming in, and that's going to be at temperature 1. And let's say we also might be adding Q. Q dot, that's a heat rate per time, and then we have a reaction that takes place and also temperature 2 and an N dot out. Okay, so let's go ahead and do just a material balance on this, and we have N dot A, and we'll use the extent of reaction. That's going to be whatever is coming in minus, and then we'll do C, that's the extent of reaction. And then let's do material balance for B as well. Okay, so let's say we had 0 coming in, this was just pure A coming in, and then let's say you have A plus B leaving. Okay, so then we have plus 2 times the extent of reaction. Okay, so there are two material balances. Now let's go ahead and do okay, so material balances. So let's do an energy balance now around the same system. Okay, so we know that we're going to start with an enthalpy 1 of our reactants, and then let's say we only have the heat of reaction at 25 degrees Celsius, but this temperature inside here, let's say it's well mixed, that's going to be equal to the outlet temperature. Now let's say the temperature is not 25 degrees. We want to get to a change from H1 to H2, and so first of all we have to go down to 25 degrees Celsius, and then we'll be able to use the delta H of reaction, and then we'll have to go back up to the final temperature. So this will be temperature 1, this will be temperature 2, and this will be 25 degrees Celsius. Okay, so we want to do the path method for this. If we use the path method, then we have delta H dot is going to be equal to NA naught, and then we have to cool that down to from T1 to 25 degrees Celsius, and we use the heat capacity of A times delta T, and then we're also going to use extent of reaction, okay, times the delta H of reaction. Okay, so if as a certain amount of moles are converted, it might be kilojoules per mole for the reaction. Okay, so if we have more moles that are converted, then this total number is going to be larger. Okay, and then let's go ahead and heat back up the products. So we're going to have some B and some A. And so we'll have to go from 25 degrees Celsius up to T2, and we'll have to use the heat capacity of B times dt, and then let's go ahead and also heat up the reaction, or the A, the unreacted amount. Okay, so there we have it, and we need to also multiply this by NB dot and then NA dot. So those are what's coming out. Okay, and this is what was coming in. Okay, so one of the things that maybe we don't know N dot B, but we had that from our material balance, so we could just substitute in here. We could substitute in 2 times XC. Okay, and then here we can substitute in our material balance as well. Okay, minus NA naught time minus XC. Okay, and so if we gave you the appropriate information for this, then you could solve for delta H. But just remember, you have to take your, in this case, reactants, okay, down to 25 degrees. You have the heat of reaction, and then your products, then you have to take them back up to the final temperature. Okay, so this is just an example, purely fictitious. A goes to 2B, but you can see how to do that with extensive reaction for material balances, and then create your energy balance as well. Now you might have a Q value that would be input as well, but delta H is going to be, this is going to go into your energy balance, and then your energy balance would have the Q in there. Okay, so let's just go back to, okay, so one of the things we want to look at is, we want to find, for example, the specific enthalpy of water at 25 degrees Celsius and 1 atmosphere. So let's just look at a caution on using the enthalpy tables, because there's a couple different enthalpy tables in the back of the book. Okay, so if we use the steam tables, this is table B5, for example. Let's just go find that. So I'm going to go back to my steam tables. Okay, and let's see if I can find B5. Okay, so there's here's B5. These are the steam tables, and so this is properties of saturated steam. And what I want to do is come down here to 25 degrees, and I'll see I have a specific enthalpy for water. Okay, it's going to be 104.8. Now this is also going to be at a pressure of 0.0317. Okay, so we might have to also use the pressure correction for this. So we have, so let's say we wanted to get it at 25. Let me write it over here to the right. We want to get the specific enthalpy of water at 25 degrees Celsius and 1 atmosphere. Okay, so this is going to be that at 25 degrees Celsius, but only at 0.0317 bar. Okay, so a lot less than an atmosphere. And so that's going to be equal to 104.8 plus a specific volume times delta pressure. Okay, so specific volume is right here. Okay, that's 0.001003. Okay, and then times a delta pressure. That's going to be about 1 bar or 1 atmosphere. Okay, so anyway, if we do the conversion there, so if we have, let's see, this is going to be meters cubed per kilogram, and then if I had times 1 atmosphere minus 0.0317 bar. Okay, when I do all the unit conversions and everything, this works out to be 1.6 0.78 times 10 to the minus 3 kilojoules per mole. Okay, and this was kilojoules per kilogram. I could convert that to kilojoules per kilogram as well, but this is going to be a very, very small number. Okay, so for liquid water, we really don't need to worry about that, so we're going to go with about 104.8. Okay, so let's go back to the slides now. Okay, so we had about 104.8, and that converted to kilojoules per mole is going to be 1.886. Okay, so let's also use this from the heat of formation. Okay, so table B1 says that heat of formation is this at 25 degrees Celsius in 1 atmosphere. Okay, so why are these two so different? One was from table B5 and the other one was from table B1. And just one caution on these are that, okay, so this was small. So that was one difference. Okay, this was at a low pressure, but we accounted for that with the VDP term, but that was going to be small. Okay, so the main issue is don't mix and match enthalpies from different tables. And so just one thing to note is that the steam tables, the reference enthalpy is that's going to be at the triple point of water, which is 0.01 degrees Celsius and 0.00611 bar. But the reference enthalpy for heat of formation is delta H of formation, for example, of hydrogen or of oxygen. Those are going to be equal to 0 at 25 degrees Celsius and 1 bar. Okay, so different references, reference enthalpies, and enthalpies are generally described as deltas anyway. So just be careful on that. Don't mix values from from different tables. Okay, so let's just look at how the enthalpy of liquid water changes with pressure at 50 degrees Celsius. Okay, so I'm going to go back to these tables, and let me go to this table B7. Okay, so this is a table properties of superheated steam. Okay, and here is 50 degrees Celsius, and let's just look at some of the water values. Okay, so we have our enthalpy right here. As we go down to different pressures, you can see that the enthalpy value, it really isn't changing that much. Okay, so maybe it's just a slight difference, 1% or so. But you really have to go up to much higher pressures. Okay, you can still see it's not changing by that much. Okay, so it really isn't a strong function of pressure. It's more of a function of temperature. So let's say we could just go up 25 degrees. You can see, and then this goes up to, this is vapor now. So phase changes and temperature, those are the big effects on enthalpy. Pressure is just a very small effect. Okay, so let's also look at its effect on vapor as well. Okay, so you can see here's the enthalpy of vapor at different pressures, and you can see, again, not a big change in the enthalpy. Okay, so just want to make that point with enthalpy is it's a function of pressure and temperature, but it's mostly a function of temperature. It's the strongest function of temperature. Okay. Okay, so let's do an energy balance with heat of formation. So we showed in that previous example, when we just have one reaction, we can use the path method. But this is going to be another method. We're going to use this when there are multiple reactions, for example. It's going to be the most common and most reliable method. Here's our our energy balances. This is with kind of batch, and this is continuous maybe. where this is per time. So put the dot over it just to mean it's per time. Okay, but what we're going to do is just compute our delta H this way. Okay, where we just sum up the molar flow rates and the specific enthalpies going out, and minus the molar flow rates and specific enthalpies coming in. Okay, so and how do we get the specific enthalpies for in or out? We can use the heat of formation method. Okay, so look at the heat of formation, 25 degrees C from, and then we'll go up from that. Okay, so this is going to be our 25 degrees, and then we can use a heat capacity to then get the change with temperature. Okay, so let's just go through. Okay, so I want to just show you a kind of a way to do this. So here's a table, for example, where we have these are going to be all the ones coming in on this side, and then these are going to be all the species going out. And so let's say you just had species A, B, C, D, and E. You would get the moles coming in, the temperature, compute a specific enthalpy, and then just compute the moles times the specific enthalpy, and then we'll add all of those up here. Okay, and do that for the out minus the in, and then that will be the change in enthalpy. Okay, so let's look at an example problem. Here we have two reactions. Now this is ammonia. It's going to be oxidized with air to form nitric oxide. Okay, so ammonia oxidized, it's going to form nitric oxide in the first step of the production of nitric acid. Okay, and these are the two principal reactions that occur. So we have a flow chart here, okay, that shows what's coming in. We have the ammonia coming in. This is at 25 degrees Celsius and 8 bar. And then we also have 900 moles per minute of air coming in. But this is much hotter, 150 degrees Celsius and 8 bar. Okay, and then we're also heating, we're putting heat into the system, here with the resistive heater, for example, and then we have product gas coming out. Okay, and so we're just saying we don't have to solve the mole balances that are given to us, but it comes out at 700 degrees Celsius and 8 bar. Okay, so what we want to do is just taking the elemental species as references. So prepare and fill out an inlet-outlet enthalpy table. Okay, so our reference species are just hydrogen, nitrogen, oxygen, and then carbon, and this will be graphite. Okay, so we'll look up in our tables for delta H of formation for all of these, and then add from our reference temperature to a final temperature, Cp dt. Okay, so that's how we're going to get the enthalpy for all of our different species. Okay, and then we'll calculate the required rate of heat transfer to or from the reactor. So we want to get the kilowatts coming in or leaving the reactor. And then so let's just go through that. I'm going to actually just come over here to okay, so we're going to do this calculation right here. As I mentioned, just summing these up, and then also computing from the heat of formation. Okay, we don't have any kinetic or potential energy changes, no shaft work, so it's just going to be delta H and Q. Okay, so we're going to compute delta H, and that's going to be equal to Q dot. Okay, so let's go back here. I'm going to build these tables. Okay, and let's just go do this in Excel. So I'm just going to walk through this. It's kind of a complicated example, but I think it's worthwhile just to see how we do this. Okay. All right, so I'm gonna go over to Excel now, and I just have a blank sheet set up. Now here are all of my species here on the left. Okay, ammonia, oxygen, nitrogen, nitric oxide, and then the water as well. And I've also gone and looked up the heat capacity coefficients A, B, C, and D. And so let me just show you where those are. So let's just look at ammonia first of all. Okay, so I'm going to go to, let's see, let me go find those. Scroll through this. Actually, I think it's right here. There it is. Okay, so it's table B1. No, B2. It's got to be B2. Okay, so here are some heat capacities. Okay, right here, and you can see ammonia. That's the first one that we're interested in, and this is going to be a gas. It's going to be form 1. Okay, so here's the form of our expression. It's just a third order polynomial, and here are the coefficients. Okay, A, B, C, and D. There's the temperature range. This is going to be in degrees Celsius. Here's our molecular weight as well. So we also want to go get, let's see, nitric oxide. Okay, there's another one. There are the coefficients. And then we had, let's just scroll down. I think we had oxygen as well. There's another one. And nitrogen. Okay, so we needed those. And then water. Okay, this is going to be the gas instead of a liquid. Okay, so we've got all of our coefficients. Let me just go back to the Excel sheet then. So we just put them in right here, A, B, C, and D, and just transfer those in. We also got our delta H of formation. So let's go back to the tables and just look at that really briefly. Okay, so we want to also get our delta H of formation, and that would actually be from table B1. Okay, so ammonia, for example, make this just a little bit bigger. Okay, so here it is. We have for liquid, and then we also have for gas. We're going to use the gas for ammonia. Okay, and then we can look at some of our other ones. Oxygen, nitrogen, those are going to be 0. Those are defined as 0. Here's nitric oxide though. Okay, and our delta H of formation. We're also going to use those numbers as well. Okay, so we had nitric oxide, there's ammonia. We also needed to look up water as well. It was going to be 0 for oxygen and nitrogen. Okay, so what we want to do now is just go ahead and start calculating the specific enthalpies. Okay, so let's just start with ammonia first of all. Okay, that's going to be equal to the delta H of formation, and then I can compute the integrate the heat capacity for each of them, and so this is just going to be A times, and then I can just put in the 25 degrees that was my reference, and then also the new temperature as well. Okay, so here's my new temperature, C14 minus 25. Those are actually equal to each other, so there's no change there. Okay, then plus, and then I'm going to put my B term in there. And then I've integrated this so that that t term is going to be t squared. Okay, so there I have my C14. I'm going to square it, minus 25 squared. Okay, I've got to divide by 2 as well. And then let me go ahead and do my C term. Okay, now this is going to be my temperature to the third, minus 25 to the third, and then that's going to be let's see, that's going to be divided by 3. Okay, and let me get my D term in there as well. There it is. Okay, and that's going to be my temperature term to the fourth minus 25 to the fourth, and then that's going to be divided by 4. Okay, so that was just going to be equal to my delta H of formation. I had no change in temperature. Now what I can do is I can just go ahead and drag this down, okay, to these other ones as well. Okay, now I don't need to do it for NO or water because those two are 0 on the inlet. Okay, but here I have my specific enthalpy. Okay, and then in order to get my enthalpy, my kilojoules per minute, not my specific, but my overall enthalpy, I'll just multiply. I'm just going to multiply these two numbers together. Okay, so I'll multiply those two together to get my kilojoules per minute. And I'll drag those down as well. Okay, so and then this is the sum of those values. Okay, and then what I want to do is just take this same formula over here for the outlet, and I will, let me just go ahead and copy this formula. I'll have to change the temperatures. Okay, I'm just going to select all of this formula and put it right here, but then I need to change that to 700 degrees instead. Okay, so I had quite a few of these references. I'll just drag each of these over and start using 700 instead for that formula for C sub P. Okay, and there I have my first one. Okay, and then I'll drag it down. Okay, this is really easy with Excel. Just drag it down. Okay, I guess I can just double click here and it'll fill down for me. Okay, so there I have my H hat, and now I want to do my specific times my molar flow rate. Okay, that's going to be 0 because I had 0 that was leaving. Go ahead and double click that as well. Okay, so this is my total enthalpy leaving, and this is in. Okay, so now my delta H is going to be the difference between those two. So I'm going to do my out minus my inlet. Okay, and that's going to be per minute. And so if I want to get kilowatts in watts, kilojoules per second, then I just have to divide this number by 60. Okay, so that's how much energy I'm going to need to remove from the system in order to keep this outlet at 700 degrees C. So we actually had to remove some. We didn't actually have to heat it. We had to cool it off. Okay, so that was a calculation for using the delta H of formation to be able to compute the change in enthalpy, and from that we were able to compute the Q value. Okay, so let's go back really quickly and review what we did today. So we did an energy balance with reactions, and the first thing that we covered was an energy balance with a single reaction, and then we looked at an energy balance with multiple reactions using the heat of formation method.